Welcome, guys. In this video, we are going to study section 4.2 on relative extrema points. These are local minimum, local maximum points, and then we are going to apply the techniques that we have learned so far to graph polynomials. We'll talk about global or absolute extrema points in section 4.4. So let's start by taking a look at the following graph. If we consider our function to be two-dimensional mountain range, then we can consider hills, tops of the hills and bottoms of the valleys as relative extrema points. So bottom of the valley here can be considered as a relative minimum point. So it doesn't mean that this point here is the smallest value attained by function on the whole mountain range over some closed interval, but this is a point, this is the smallest point in some vicinity near that point. And similar for the tops of hills to be relative maximum points. So for instance, this point here is a relative maximum point. It doesn't mean that it's the largest point, largest value attained by function as a whole on some closed interval, but rather this is the largest point if we consider some open interval around this point here. So let's formalize definition for relative extrema points. Function f is said to have a relative maximum at x0 if there is an open interval containing x0 on which f at x0 is the largest value. That is, f at x0 is greater or equal than f of x, where x is any x in that open interval. Similarly, f is said to have a relative minimum at x0 if there is an open interval containing x0 on which f at x0 is the smallest value. That is, f at x0 is less or equal than f at x for all x in that open interval. Then if f has either a relative maximum or relative minimum at x0, then f is said to have relative extremum at x0. So as we said before, if we are looking at relative maximum point, for instance, here, then this is largest value attained by function on some open interval surrounding this value x0. All right. Let's study the following graph. Here we can see that function has several relative extrema points. So we see function attaining relative maximum at those 3 points and relative minima at these 2 points. So if we pay closer attention to these points there, we can see that relative extrema points are happening either at points where tangent line to the graph is horizontal to x-axis, or in other words, f prime at that point x is equal to 0, or at a couple of points here we see that our function at these points is not differentiable. So these are a couple of corner points where a function is not differentiable. So relative extrema points are happening either at points where first derivative is 0 or the derivative of function doesn't exist at these points. So we can formalize that by the following theorem. First, to distinguish between these two types of points, let's introduce the following definition. So we call points where the first derivative of function is equal to 0 as stationary points. So such points x, such that f prime at x is equal to 0, these are called stationary points. And points where either derivative of function is equal to 0 or derivative doesn't exist, or points where our function is non-differentiable, so let's call this points of non-differentiability. We call these two types of points as critical points. So stationary points are a special case of critical points. Now, we have seen that all relative extrema points are happening at critical points, and the following theorem is going to formalize that. Suppose that function f defined on an open interval containing point x0, if f has a relative extremum at x is equal to x0, then x is equal to x0 is a critical point of f. That is either the slope of tangent line is equal to 0 at that point, or function f is not differentiable at x0. Let's find all critical points of the following function. So we need to find points where our function is not differentiable or first derivative is equal to 0. So let's find first derivative of this function, which is equal to 5 over 3 multiplied by 3. So this is 5x to the power of 2 over 3 minus this is 10x to the power of minus 1 over 3. And now bringing that to common denominator, we'll have 5x minus 10 over x to the power of 1 over 3. So we see that x is equal to 2 is a stationary point. And at point x is equal to 0, our function is not differentiable. So two critical points that we have found are x is equal to 2 and x is equal to 0. And if we take a look at the plot of this function, we can confirm that. So we see that somewhere here at x is equal to 2, we have stationary point, and at point x is equal to 0, we have a corner point where our function is not differentiable. And also, following our previous theorem, we see that relative extrema points are, so here we have relative maximum point and relative minimum point at x is equal to 2. We see that relative extrema points are happening at critical points. Now we know that relative extrema points must occur at critical points, but it doesn't necessarily mean that all critical points are points of relative extrema. So for instance, if we study the following graph at the bottom row, these 4 graphs indicate critical points at which we do not have relative minimum or relative maximum. So let's study a bit more in detail the following 8 graphs. So in the first graph, x0 is a critical point. F prime changes its sign over x0, so our function is increasing up to point x0, then it is decreasing after point x0. In this case, we have a point where our function is not non-differentiable, and before x0, our graph is our function is increasing, and after that point, our function is decreasing. In this case, we have a relative minimum point, and our function is decreasing up to point x0, which is a stationary point, and increasing after this x0 point. And similar for this case, it's decreasing, then increasing, and at x0, we have a corner point where our function is non-differentiable. So first row indicates critical points over which f prime changes its sign, and we see that at all these 4 cases, we have relative extrema. And second row, we have 4 critical points over which f prime doesn't change its sign. So in first case, our function is increasing up to x0, and it still keeps increasing after x0. In this graph, we again have stationary point at which our function is decreasing up to x0, and it keeps decreasing after x0. So no relative extrema in that case. In this case, we have vertical tangency. At x0, our function is increasing up to x0, and it keeps increasing after x0. And similar, in the last graph here, we have again vertical tangency, and f prime doesn't change its sign again in this case, which suggests us the following theorem. So first of all, we should note that function f has relative extremum at those critical points where f prime changes its sign. Moreover, by looking at the sign of f prime, we can decide whether we have relative minimum or relative maximum happening at our critical point. So in first case here, our f prime is changing its sign, so it is increasing up to point x0. So f prime is positive to the left of x0, and it is decreasing after x0, so it's negative. F prime is negative after point x0. So in this case, we have relative maximum happening at that x0 point. Similar in this case, f prime is positive up to x0, negative after this point. So we again have relative maximum case. In this case, in the third graph here, our f prime has negative sign. So it is, our function is decreasing, a negative sign up to point x0. And after point x0, it's increasing. So f prime has a positive sign, meaning that at point x0, we have relative minimum point. And similar in the last graph, f prime has negative sign up to x0 and positive after x0. So we have relative minimum happening at that point. Our findings are summarized in the following theorem known as first derivative test, which allows us to find relative minimum, relative maximum points by studying the change of sign of f prime over critical points. Suppose that function f is continuous at a critical point x0. If the sign of first derivative is positive on an open interval extending left from x0, so let's assume that we have critical point x0 somewhere here. And if f prime, the sign of f prime is positive on the left and negative on the right on some open interval extending right from x0, then since our function is increasing up to some maximum value at x0 and then decreasing after x0, then at this point we have relative maximum point. And similarly, in part B, if our function is decreasing on some open interval extending to the left from x0, so our function is decreasing, then it attains its minimum value at x0. And if it is increasing on some open interval extending to the right from x0, then at this point we have relative minimum point. And as we said before, if f prime doesn't change its sign over critical point, then for instance, if our function is increasing up to point x0 and increasing again afterwards, or decreasing up to point x0 and decreasing afterwards, then in this case, we have no relative extrema point. Now let's come back to the problems that we solved previously. So we found critical points of the following function, namely x is equal to 0 and x is equal to 2. Now let's study the sign of f prime to find relative extrema points without looking at the graph of this function. So we have two critical points at 0 and 2. Now, the multiplicity of roots is 1 for x is equal to 2, and multiplicity of x is equal to 0 is also odd. 1 is 1 over 3. Now, if we substitute plus infinity, we'll get plus plus. So f prime is positive on interval from 2 to plus infinity. Now, both of these roots have odd multiplicity, so the sign will alternate. And we can see that our function is increasing up to 0.0, decreasing from 0 to 2, and increasing again from 2 to plus infinity, meaning that at point x is equal to 0, we have relative maxima point and relative minimum at point x is equal to 2. And we can confirm that by looking at graph of our function now. So relative maximum at point x is equal to 0 and relative minimum at x is equal to 2. Another useful observation that we can make in case when we are working with stationary points is that if we have a stationary point and the graph is concave down, then this point is a point of relative maximum. This is true since by one of the definitions of concavity, concave down function lies below of all of its tangent lines, meaning that the whole graph will lie below its tangent line at the point x0, which is, let's say, a stationary point, meaning that we'll have a relative maximum in this case. So this theorem, which is called a second derivative test, summarizes these findings. Suppose that function f is twice differentiable at the point x0. If f prime at x0 is equal to 0, so we have stationary point and second derivative is positive, or our function is concave up at that point, then f has a relative minimum at x0. And if first derivative is 0 and second derivative is negative, so our function is concave down at that point, then our function has a relative maximum at x0. And in case when both first and second derivatives are 0, then the test is inconclusive, meaning that we can have either relative maxima, relative minima, or no relative extrema at all at that point x0. Second derivative test, if we compare it to first derivative test, it's an useful tool to make quick decisions about relative extrema at the stationary point. But first derivative test is more useful since it covers a broader range of cases. Second derivative test, for instance, can only be applied to stationary points, and it also gives you inconclusive results in case when second derivative is also 0. Let's find the relative extrema of the following polynomial, and let's try to apply second derivative test this time. So first, let's find first derivative. This is 15x to the power of 4 minus 15x squared, which is further factored out as 15x squared. We'll be left with x squared minus 1, and which in turn is factored as x minus 1, x plus 1. Second derivative is equal to 60x cubed minus 30x, factoring out 30x. We'll be left with 2x squared minus 1. Now let's, so we have three stationary points, x is equal to 1, x is equal to 0, x is equal to 1, and x is equal to minus 1. Now let's check the sign of second derivative at these stationary points. So if we substitute minus 1 here, this is positive, this is negative. So sine of second derivative is negative. At point x is equal to -1, meaning that our function is concave down. So according to second derivative test, in this case, we have relative maximum point. When x is equal to 0, our second derivative is equal to 0, so our test here is inconclusive. And if we substitute x is equal to 1, this is positive, this is positive. So the sign here is positive, meaning that our function is concave up at point x is equal to 1. So we have a relative minimum at point x is equal to 1. All right, so since our test was inconclusive at point x is equal to 0, then we have to use first derivative test. So we have to study signs of f prime to find what kind of extrema point we have at x is equal to 0. So we have three stationary points, x is equal to -1, multiplicity is 1, at x is equal to 0, multiplicity is 2, so the sign will not change over this stationary point. At x is equal to 1, multiplicity is 1. So if we substitute plus infinity, this is positive or is positive. So this is plus, multiplicity here is odd, sign will alternate, minus. At point x is equal to 0, multiplicity is even, so the sign will not change, and over 1 over -1, odd multiplicity, so the sign will alternate, meaning that at point x is equal to 0, since our function is decreasing and then continues to decrease over point x0, at point x0 we have no relative extrema. In the rest of this video, we are going to study ways to analyze and graph polynomials. However, the techniques that we'll be using to graph polynomials can be used for other functions, and we will see that in later videos. So before proceeding, let's quickly recall a couple of facts about multiplicity of roots of polynomials. First of all, we call root x is equal to r as a root of multiplicity of m for a polynomial p of x, in case when our polynomial p of x can be factored out as x minus r to the power of m multiplied by some q of x, where q of x is also a polynomial and x minus r does not divide q of x. Let's summarize our findings about multiplicity of roots of polynomial to study the behavior of polynomials near its roots. In case when we have even multiplicity, then as we can see in the following two graphs here, when we have even multiplicity, the graph of polynomial does not cross x-axis. Well, it intersects it at once at that root x is equal to r, but doesn't cross it. Also, x-axis is tangent to our polynomial. So basically, x-axis works as a tangent line to our polynomial at point x is equal to r. And as we can see here, concavity doesn't change over that root, and we don't have inflection point here. In case, as a couple of graphs here, when we have even odd multiplicity greater than 1 or 3 or more, then our graph is tangent to the x-axis. So basically, our x-axis works as a tangent line to our graph. And also, as we can see, in case of odd multiplicity, our graph crosses this root, so it crosses x-axis. Also, as we can see, the concavity of our function changes, and we have an inflection point. To confirm all these findings, guys, you can, to prove them, you can start by taking derivative, for instance, of that expressions and taking notes that this is odd or even. You can then find second derivative and factor out x minus r and see how the sign of second derivative changes to confirm these findings. Now, in case when we have simple roots, so we call simple roots as roots of multiplicity equal to 1, then as we can see here, the graph is not tangent to the x-axis, and our graph crosses x-axis. And in case of simple roots, our concavity might change or might not change. So both of these things may happen. And we don't know whether it has or doesn't have an inflection point here. Let's study the multiplicity of roots of the following polynomial, and let's make conjectures about behavior of this polynomial near its roots. So we can see that x is equal to 0 has odd multiplicity greater than 1, meaning that our function is going to cross x-axis at x is equal to 0, and the concavity will change here. So we'll have inflection point, and also our function is going to cross x-axis. For x is equal to 4/3, we have simple root here, and all we know is that our function is going to cross x-axis. In case of x is equal to -2, here we have even multiplicity, and we know that we'll have no inflection point here. And our graph will not cross the x-axis. So now let's take a look at the plot of this polynomial and confirm our findings. So we said that at x is equal to 0, we have odd multiplicity, and as we can see, our function crosses the x-axis, and concavity here changes from being concave up to being concave down after x is equal to 0. At x is equal to -2, we have no inflection point. Our graph is concave up here, and our graph does not cross x-axis. And in case of simple root at 4/3, our graph crosses x-axis, and it happens that in this case, concavity doesn't change. All right, so finally, let's sketch the following polynomial without the help of software. So sketching polynomials is one of the easiest tasks, since polynomials are continuous everywhere. They are differentiable everywhere. Their domain is from -infinity to +infinity. They have no horizontal asymptotes, meaning that their end behavior is that they are going to increase or decrease without bounds. Also, a polynomial of degree n will have at most n roots. It will have at most n-1 points, critical points or stationary points in the case with polynomials, since polynomials differentiable everywhere. So all its critical points are stationary points. Also, the total number of inflection points is no bigger than n-2. Since if we have a polynomial of degree n, then first derivative will have will be a polynomial of degree n minus 1, meaning that it will have at most n minus 1 roots, and second derivative of this polynomial will have at most n minus 2 roots, since second derivative will be a polynomial of degree n minus 2. All right, now let's sketch our polynomial here and let's compare it to the actual plot of this polynomial. So first, let's find x-intercepts. So x-intercepts are given as follows. Let's try to factor this out. Let's write this down: x cubed minus x minus 2, x minus 1. Now let's factor out x minus 1. So we'll have x plus 1 minus 2. So this is x minus 1, x squared plus x minus 2. Roots of this are minus 2 and 1. So our root x is equal to 1 has multiplicity of 2. And second, another root is x is equal to minus 2. Now, from the multiplicity of roots, we know that our function is going to intersect our x-axis at points x is equal to 1 and x is equal to minus 2. Root x is equal to 1 has even multiplicity, meaning that the concavity will not change at that point. Also, our function will not cross x-axis at x is equal to 1. At x is equal to minus 2, we have simple root, meaning that our function will cross x-axis, and we cannot decide whether it will have an inflection point at x is equal to minus 2 or no. We'll find this out later when we'll find second derivative of our polynomial. Then we need to find y-intercepts. Okay, so to find y-intercepts, we'll substitute value of x is equal to 0. So when x is equal to 0, our y is equal to 2. So y-intercept is at 0, 2. Okay. Now let's study end behavior of our polynomial. When x goes to infinity, limit of our polynomial will go also to plus infinity. So y will also go to plus infinity. When x goes to minus infinity, we see that the highest degree term here, highest power term here is of odd multiplicity, meaning that y will go to minus infinity. Okay, so this is for end behavior. Now let's find derivatives. So first derivative is given as 3x squared minus 3. So factoring out 3, this is x minus 1, x plus 1. All right, so now let's study the signs of f prime. So we have two stationary points at minus 1 and 1. So multiplicity of roots here is odd. If we substitute plus infinity, this is plus, this is minus, this is plus. So our function is increasing from minus infinity to minus 1, then it decreases from minus 1 to 1, and then it increases again from 1 to plus infinity. Let's find second derivative. To study the concavity of our function and find possible inflection points. This is 6x, meaning that we have an inflection point at x is equal to 0. So if we study signs of f double prime, then it is positive from 0 to plus infinity, meaning that our function is concave up from 0 to plus infinity, and it is concave down from minus infinity to 0. All right, now we are ready to make a sketch of our function. Okay, so let me add the axis. This is our y-axis. This is our x-axis. Now let's indicate our x-intercepts at -2 and at x is equal to 1. We have y-intercept at point y is equal to 2. Okay, so what do we know now? We know that our function is decreasing without bound when x goes to minus infinity, and our function is concave down up to point x is equal to 0. All right, so let's sketch that. Using this color, for instance. Okay. Now, at point x is equal to -2, we have simple roots, so our function is going to cross x-axis. Then what do we have to look for is that our function is increasing up to point x is equal to -1. At point x is equal to -1, we have stationary point. Let's just in case find a y coordinate of our stationary point. So if we substitute -1 here, we'll get -1 plus 3 plus 2. So this is 4. So somewhere here. So our function is concave down and it is increasing up to point x is equal to -1. At point x is equal to -1, we have stationary point, after which our function is decreasing up to point x is equal to 1. Let's find y coordinates of x is equal to 1. If we substitute 1 here, this is 1 minus 3 plus 2. So this is 0. Oh, yes, at point x is equal to 1, we have x-intercept, right? Also, our concavity changes at point 0 from concave up to concave down. So our graph will look something like that. So it's concave down, so it should have been more smoother, but that's fine. And at point y is equal to 2, our function is going to intercept y-axis, after which it is concave up now. Okay, at point x is equal to 1, we have even multiplicity, and our function will not change its concavity, and our function will start to increase without bound as x goes to plus infinity. Okay, so our graph will look something like that. Now let's confirm that by looking at the actual plot of this polynomial. Okay, so now we can apply the following techniques to study the behavior of function and to make a plot of it without using software.